So today we're going to talk about the polarization of light. So light is polarized when the electric fields oscillate in a single plane. So we're talking about the direction that the electric field is oscillating. And for the picture below, you can see someone moving a rope in a polarized manner. So the electric field could be vertically polarized or horizontally polarized, as is shown in the picture. Unpolarized light, like light that's coming from the sun or from a light bulb, has random orientations of E. So remember, the electric field is always perpendicular to the direction that the light is moving, but it can be pointing at any direction in the plane. So on average, there's equal amounts of the electric field polarized in any given direction. A polarizer is a material through which light can only pass with its polarization in one direction. So if you look at the picture on the right, you have a vertically polarized rope going through a slit that's also vertical, and so the light can get, so that the wave in that rope can get through it. Similarly, for a light wave, if the electric field is parallel to the polarization axis, then it can get through it. If you flip it so that the direction of polarization is perpendicular to the opening, then that's like the picture shown in B. So you've got that rope trying to oscillate through a slit that's perpendicular to it, and it just can't do it. So electric field perpendicular to the polarizer direction is going to be blocked. So only the component of the electric field that's parallel to the polarization axis will be transmitted. And so if the incoming light is polarized in a planar manner, so that it's all in one direction, then the outgoing intensity of the light is equal to the incoming intensity times the cosine squared of the angle between the polarizer axis and the electric field direction. So the electric field points in the direction shown in the picture at the left. So it's at an angle to the polarization angle, an angle of theta. So the component of the electric field that gets through is equal to E0 times the cosine, because it's adjacent. So E0 cos theta gets through, is E0 sine theta does not get through. And the intensity is proportional to the electric field squared. And so that's why we get the cosine squared of the angle. So the amount of the light that goes through, the intensity of the light going through, is proportional to the cosine squared of the angle between the direction of the electric field and the polarizer angle. If we have unpolarized light shining through a polarizer, remember it's completely random coming in, so on average, half of the electric field is going to be vertical, half of it's going to be horizontal, so half of it will be blocked and half of it will get through. So when unpolarized light hits a polarizer, 50% of the light will get through it. So if we have initially unpolarized light hitting two polarizers, the first one is vertical and the second one is horizontal, what's going to happen is that the unpolarized light is going to hit the first polarizer, and it's going to get half of it coming through. So the intensity is going to go to I0 over 2, and all the light that goes through is going to be polarized in the same direction as the polarizer axis, so vertically. When it hits the second polarizer, now all the light is vertical, the polarizer is horizontal, so all the light is perpendicular to the second polarizer angle, and so no light is going to get through. So when you have cross polarizers, no light can get through. What happens if I've got polarizers that are crossed and I put in a third polarizer? So in example 1, the light that gets through the first polarizer is going to be horizontally polarized. Nothing's going to get through the second one. In situation 2, the light that gets through the first polarizer is horizontally polarized, and then some of it is parallel and some of it's perpendicular to the second polarizer axis. So a little bit of it's going to get through, and then some of that light is parallel to the third polarizer axis, and so some light, a very small fraction of the light, is going to get through that third polarizer, even though it's perpendicular to the first polarizer. So if I put a third polarizer in between two cross polarizers and I rotate it slightly, then I can get different intensities of light coming out. But if I have the two cross polarizers one right after the other, then no light will get through it. All right, so let's say I have vertically polarized light that has an intensity of 515 watts per square meter, and it passes through a series of 3 polarizers. So I've got my light that's coming in. I0 is 515 watts per square meter, and this is a very typical problem to show up on a test. It's sort of a simple calculation problem that you should be able to do. The first polarizer is at 10 degrees to the vertical. All right, so the angle is 10 degrees. The second polarizer is at 45 degrees to vertical. And then the third polarizer is at 90 degrees to the vertical. All right, so I want to know what intensity of light comes through the final polarizer. So what I'm going to have to do is I'm going to have to calculate what intensity of light comes through each one after the other, until I get out the far side. All right, so what's the intensity of light through the first polarizer? Well, it's going to be I0 times cos squared of the angle between the light that's incident and the light that gets through. So let me switch colors so we can see what's going on. So I've got light that's vertical, hitting that polarizer. The angle between it and the polarizer angle is 10 degrees. So it's going to be the cosine of 10 squared. Remember, to do cos squared, you take the cosine of 10 and then I square it. So it's going to be 515 cos squared of 10, and I get 499.5. And the units for intensity is watts per square meter. So now I've got light in between polarizer 1 and 2. It's going to be at an angle of 10 degrees. Drawn that a little bit too slanted, so let's draw it on here. So it's going to be at an angle of 10 degrees. And the next polarizer axis is at 45 degrees to the vertical. So the angle between the two polarizers is the angle that I need to take the cosine of. So it's theta 2 minus theta 1. So 45 minus 10, which is 35 degrees. So I2 is going to be I1 times the cosine of 35 squared. And so that's going to be 335.15 watts per square meter. Okay, so now I've got light in between those two that's at 45 degrees to the vertical. And now I'm going to shine it on the final polarizer. So the intensity that gets through is going to be the intensity incident, I2, times the cosine now of the angle between the incident light, which is at 45 degrees, and the polarizer axis, which is 90 degrees. Angle between those, 90 minus 45, is 45. Okay, so it's going to be cos squared of 45. Put that in the calculator, so I've got 335.15 times cos squared 45, and I get 167.6 or 168 watts per square meter is going to be the intensity coming out the third polarizer. So just remember, as you go through, it's the angle between the incident light and the polarizer axis that you need to take the cosine of. We can also get polarization by reflection. So when light is reflected from a non-metallic surface, it comes off polarized, and it has a fraction of the fraction of the polarization angle parallel to the surface. As you change the angle, more and more of the light becomes polarized parallel to the surface until you're at a specific angle called Brewster's angle, at which all the light is polarized parallel to the surface. And experimentally, we find that Brewster's angle is equal to the angle at which the index of refraction for the material it's going into, so for example water, divided by the index of refraction of the material it's coming from, typically air, so that would be 1. The tangent of Brewster's angle is N2 over N1. So if I do a quick example, what's Brewster's angle for light reflecting off water? Well, in that case, we've got N1 is air, N2 is water, 1.33. And so the tangent of the angle is going to be 1.33 divided by 1. And so Brewster's angle is going to be the inverse tan of 1.33, or 44.8 degrees. All right, so what I want you to do today is to do a practice problem where you have light going through multiple polarizers. So you start off with initially unpolarized light with an intensity of 100 watts per square meter. It goes first through a vertical polarizer and then through polarizers that are at the angles shown. And you need to calculate what's the intensity after each polarizer. So I1, I2, I3, and I4.